All right. Hi. Welcome to part five actually now, of exam three. That's what I meant to say. And so we went through and we worked through the first four parts here that we have shown on screen, where in the first part we explained the Lewis relation. Second part, we explained the Lewis relationship and how it can be used in energy balance to determine the relative humidity from the wet and dry bulb temperatures. We also went on to part three, where we explained the relationship between the adiabatic saturation temperature and the wet bulb temperature, and we pretty much just showed how the equations are similar. And in the last part, we derived the differential equations that we're going to be using in this part of the exam between the differential equations between moles fraction of water vapor and the temperatures of the air and the water in the cooling tower. Excuse me. So in this part, we're actually going through and coding and figuring out how we can code to solve part B2, part 5 of this exam. And so through this, we're really going to be using the concepts that we took for part 4, and we're going to take them and put them into an actual real-life problem for part 5. And that problem is given to us, and we're going to solve the differential equations derived in B1 for a 20-meter tall cooling tower, where the air-water heat transfer coefficient is 10 watts per meter squared Kelvin. The specific area is 5 meters squares per meter cubed, which is by area by volume basis. If you can hear my dogs upstairs, I do apologize. I just don't know if my mic will pick that up. Hot water enters from the top at 70 Celsius with a flow rate of 0.5 kilograms per meter squared seconds. Air enters from the bottom with a velocity of 5 meters per second at a temperature and relative humidity of 25 Celsius and 50% respectively. And then we make plots of the water temperature, air temperature, and the water pressure as a function of position in the cooling tower, which is pretty similar to what we did in our last exam when we were coding, and making a 3D plot of how we wanted that to set up. And so I went ahead and brought in some important things that we're going to be needing for solving this equation and this problem, just to save a lot of time, because honestly this would have taken probably 10 to 15 minutes in general just to put in and explain that each time I did this video. So I can go through quickly and walk through it, but I just did not feel like it would be very time efficient to go ahead and record myself putting all this in, because it's pretty much given information. We pretty much, all of these we've already used multiple times in our exams. NumPy is numerical Python. It allows us to solve equations. Plotly subplots, we can make subplots. That just allows us to make graphs and then use other sort of plots depending on what we want it to look like. Plotly.io as Pio allows us to pretty much modify that subplot or that graph, whatever we're trying to import in. It just allows us to modify that, such as like what I did with the next line, where from that library of plotly.io, I'm just using the default background of Plotly Dark, and that's just really to help us see the points a lot better on the graph when we come in around to do it. I did this on the last exam too, just it makes it a lot prettier. SciPy integrate, solve IVP, so that just pretty much solves the individual value problems from the SciPy integrate library. And pretty much the same thing for the next one, SciPy Optimize. From the SciPy Optimize library, we're importing root, which is pretty much just a root solver that we're going to have to use for when we want to converge the air feeds of the two. And so getting into this next part of after we imported all of our libraries, we are looking at this equation that I went ahead and put in. And it might not be inherently obvious what it is and what we're trying to do, but we're taking this input value of t and we're putting it into the Antoine equation, which will give us the saturated pressure values for whatever we are looking at that temperature. And so this is pretty much what this is going to be spitting out for whatever value of t that we want to put in here. And we want to call this equation. We can input that value of t, and we'll come up here, do the Antoine equation, give us in return the saturated pressure value. Outside of that, I also brought in all the givens from the problem that was stated previously. I'll walk through those really quick, where the heat transfer coefficient is 10, gas constant is 8.314, the density of air is 1.2, the heat capacity of air is 1,000, the heat capacity of water vapor is 2,000, and the heat capacity of the water as a liquid is 4,190. The heat of vaporization is 40,700. And this is the equation that I went ahead and put in for calculating the mass transfer coefficient, which is equal to the heat transfer coefficient divided by the density of the air multiplied by the heat capacity of the air. We were also given the specific area, which is 5, the molecular weight of water, which is in kilograms per mole, as well as the molecular weight of air, which is also in kilograms per mole. We were also provided with the velocity, which is 5 meters per second, the liquid flow rate, which is 0.5, and the pressure of the system, which is 101,325, which is for the ideal gas, pretty much what it associates with. And we're also given that the height of the cooling tower that we're going to be working with is 20 meters. So those are all the givens pretty much that we have provided to us. So we're going to go in and start by one, modifying the inlet temperature feeds, because I know that's not in Kelvin. We're going to have to add some values to that. And we're also going to have to get our initial guesses put in for the mole fraction of water, as well as the temperature gas outlet for the temperature of the gas, really. So we're going to take those two guesses and put those in, as well as modify some stuff previously that we already have put in, before we can actually get in and solve this problem. And so the first thing that we're going to do is we're going to create a linear z-plot, which is pretty much just going to be a array pretty much of linear placed values of that plot. And so this is going to be using to pretty much get a different or an evenly spaced out area based on the height, which is 20. And we're going to say we want 21 values for that. So we're going to get a value roughly every 0.909 meters. We want to get one roughly about every meter, and that's going to help us track it throughout the cooling tower, how well that's going to work as we use that in the future. And so next thing we're going to have to do is we're going to have to alternate the water feed that we were given, and that was, I have it right off to the side here, 70 degrees Celsius, and we're going to have to add 273.15 degrees to make that into Kelvin. And we're going to have to do the exact same thing with the gas feed. So I think that one was 20. We're still going to have to add 273.15 degrees Kelvin on that. Just degrees in general, just make that into Kelvin. So now, before we make our guesses, we also still have to make the mole fraction of the water feed that's going in. And we have this value from previously when we were working through this equation. And so that is going to be 0.5 times the heat of vaporization, which is, I have that in HV, yeah, first one's capitalized, multiplied by the heat of vaporization. This is going to be all multiplied by the temperature of the air feed that we adjusted for Kelvin. Let me clean this up. Yeah, so now it's calling TA feed. And so now we need to do that, and then we can also divide that whole numerator, where I'm going to add another set of parentheses. And we're going to divide this whole thing by the total pressure, which is 101,325. Nope, not PA. So that's how we're going to find the mole fraction of our Y feed. And then we can also need to find the total flow rate of the air, the gas flow rate of the air. And that's going to be equal to the total pressure multiplied by the molecular weight of the air. And this is going to be all divided, this numerator. This is going to be divided by the gas rate constant, which is 8.314, multiplied by the temperature of the air feed. And then this whole equation here is going to be multiplied by the velocity. So I'm going to put another set of parentheses, and this is all multiplied by velocity, which I'm pretty sure that's no. Yes, that was right there. So I just want to make sure that there wasn't capitalizations in that. So now we have this set up. So we have our correct inlet and outlet feeds in terms of temperature. We are able to calculate our mole fraction of the feed and water. We also have the gas flow rate of the air. And so now that we have this, we need to go through and set up and figure out our initial guesses that we want to use for when we start solving this in the next part of it. But we don't really want it to be too far off. So what we're going to do here is, don't want to capitalize now. I won't make that capitalized. So I just want to make this guess. So we're going to be using y out underscore guess as that placeholder variable. And so that's pretty much just going to be holding in our guess that we're going to use for when we want the equation that we're going to have for the differentials to converge to this certain point or around a certain point. And so that's going to be our initial guess that we're going to be putting in. We know it's going to be off because we need to add in another equation later down the road that allows us to converge to the desired and the correct values. But this is what we're going to have to use for now. And so to account for that error, I'm going to just take what the value we have for the mole fraction feet of the air, which is right here, this little equation here that we can calculate. And we're just going to multiply that by 1.1. That way it's not too high, it's not too low, it's not very far off. It's just accounting for a little bit of potential error. And then the other thing we got to do is we also need to do a guess for our temperature of our gas in the out phase, or on the outlet. Oh, it'd be helpful if I could spell guess. So that is going to be pretty much multiplied by the same thing, but except it's going to be the temperature of the feed of the gas. And then we're just going to add about 5 degrees Kelvin just to make that line up. So, pretty sure, I just want to make sure this is called back to, yep, and yep. Okay. So those are both working and calling back to the right variables. That's why I always just want to double check because I know capitalizations and all that, it's annoying to deal with. So we're pretty much done with this portion of it. The last thing that we want to do, and this will come back to help us later, is that we want to lock solution so that there is none. And really all this is doing, I want to shift enter while this is running. Perfect. Okay, ran up with no errors. Perfect. So pretty much all it is doing is it's locking the variable solution, so we don't have to go over and have our overarching issues with that when we go into this next part of the code that we're going to write. And so what we're going to do here in this next part is that we're going to start and develop our equation that we are going to use for finding the differentials of each equation, pretty much kind of what we did in part 4 of it. And so the first thing that we need to do is that we need to define the actual equation, that name that we want to use. And so I'm pretty much just going to use, because we know it's what we're using it for, the differential of finding the temperature of the water and the temperature of the gas. And pretty much our inlet variables are, we're going to use Z, which is our location up and down the cooling pipe, as well as V as our inlet variables. And so now that we have this, we need to store these, what we really want into these values of V, the array of B. And so the first variable that we're going to be looking at is just Y itself, the mole fraction of water. And we're going to go ahead and just store this in the first location in the variable of the array. And so that's what's denoted in, V naught, which is just the first location of the array. So the next the next variable that we're going to be looking at is going to be the temperature of the water, and we're going to store that into the second value in that same array. And then we're also going to do the same thing with the temperature of the gas, where we're going to store that in the third value of that array. And so now that we have this, we are storing our first 3 values that we're actually looking for the differentials: the mole fraction, the temperature of the water, and the temperature of the gas. These are all going to be stored in these first 3 locations in the array, and we can call them by referring to the array in that way. And so the first thing that we got to do, and we got to do this to really get to the values of the differential equations and program the differential equations so we can have them work in the way that we want them to, is that we're going to have to find the gas flow rate of the water vapor that's in the air. And so that can be pretty much programmed and it's pretty straightforward, pretty much like we did last time in part 4, how we got it and where this equation comes from. So this will be the total mole fraction of the water that's in there minus 1 over the same value, just whatever's remaining, because it's only coming from water, and then the water's going to a gas vapor phase. So that's where this is coming from. And then you're going to want this whole fraction that's going to end up coming out of here. It's going to be multiplied by the gas flow rate of the air. And then you're also going to want to multiply by the molecular weight of water and divide by the molecular weight of air again. And so that's just going to account for the gas flow rate of the air. And that's pretty much just going to account that for when we just want the only, no, that's not right, is it? Yeah, that needs to be, oh, sorry, let me just make sure that all these variables are so good. Do I have G here being referred to? Yeah, okay. I just want to make sure everything was good with that. So yeah, once again, that's just going to discount for the gas flow rate of the air, so we can only have the gas flow rate of the water. And so the next thing that we are going to need to do is that we can go ahead and make our equation that equates the total gas flow rate of air within the whole entirety of the cooling tower is just going to be that same flow rate plus the flow rate of the air. What did that do? I don't know, it looked like it messed up the above equation a little bit, but I don't think anything's wrong with it. I guess we'll see when we run, to be honest. But so yeah, that just pretty much allows you to get the total gas flow rate of the whole entire system of the cooling tower. And so after this, we can go ahead and find the average molecular weight, which is what we also want to do, which is going to be the total gas flow rate, which will be pretty much just G at this point. This will be divided by G air. So this will be divided by the gas flow rate of the air divided by the gas flow rate of the molecular weight of the air. And this will be also being divided by the summation of whatever else is going to be on to it, which is the gas flow rate of the water divided by the molecular weight of water. So that's pretty much just taking it and putting it into a concentration form. And do I need another parentheses? No, I don't. So that's just pretty much an easy way of how we are going to be getting the average molecular weight to be used also in this part of the coding. And so the last thing that we really need to do before we can go into and start actually putting in any equations that we got and developed and derived from part 4 is that we also need to get the heat capacity of the gas phase of whenever we are calculating it as well. So that's going to be solved by the heat capacity of the air multiplied by the gas flow rate of the air, also added on to the heat capacity of the water vapor phase, which I just want to make sure that we got all these so far. Yeah. So all those values are correct, and then this is going to be multiplied by the gas flow rate of the vapor phase, which is still good. And then we just need to divide this whole thing by the gas flow rate of air. Oh, excuse me 1 second. I'm going to need to go on my nose. Suck it up. So that gives us the heat capacity of the gas phase, the gas vapor phase that we were using. And so now we can actually go in and put in our set of equations that we derived from part 4. And so the first thing that we're going to be putting in is going to be the molar flux of water. And so we found this in part 4 to be the mass transfer coefficient divided by the gas constant divided by the temperature of the gas. I don't think that's what I used. Where is it? Something doesn't look right. Oh, that's why. I was so confused because I knew I was using that value somewhere, but I wasn't seeing it up here. I'm like, I knew I put this in. Okay, so we're actually good. So I was looking for that temperature of the gas constant, where we were storing that, but we're okay. So we're going to have those be divided by each other, and then we're going to have to multiply that by the saturation value of the temperature of the water, which we're going to end up calling our equation, for our Antoine equation like we did previously. And so that's going to be what we call N. And then, but we're going to have to subtract as well the mole fraction of water multiplied by the total pressure. And that will end up giving us our molecular weight that we desire. Not our molecular weight, sorry. Our molar flux that we desire of the water. And so now that we have that, we can also add in our equation for the differential of y, which is the change in the mole fraction of water as it transfers through whatever, but we don't have it with respect to dz right now. So we're just going to have it as, at least not, we do have it in respect to dz in terms of the equation, but I'm not going to have it in terms of dz when referring to the variable because it's easier. So this is going to be the negative of a multiplied, or the negative specific area. And remember, this negative is because when we're looking at the actual problem itself, the z orientation is increasing as it goes downward. So we do have to keep that negative. And so we'll be doing that multiplied by the total average molecular weight we've calculated right above it. And we're going to divide by the gas constant, or the total gas flow rate, multiplied by that molar flux of water. And that'll give us our first differential that we derived back in part 4 of this. Now we need to go through and derive the other two. So the second one is going to be the change in temperature of the water with respect to the cooling tower and where that's going to be going. And so that is going to be the specific area that we calculated previously divided by the liquid flow rate. Sound like Elmer Fudd there for a second. So that's going to be divided by the liquid flow rate. That's going to be divided by the, I think that's the right variable. Capital L. I knew it was wrong somewhere. Multiplied by divided by the heat capacity of the liquid water vapor phase. And so this is going to be all multiplied by, That's not what I want either. That's what I want. It's going to be all multiplied by the heat transfer coefficient, multiplied by the change in temperatures between the gas and the water. And this is going to be subtracted by that that second set of values and variables that we had previously, where I explained how this is going to have to be added on to account for the heat and vapor and the mass lost for evaporation through this transfer. And so as the hot water transfers down the tube and through the cooling tower, it's going to be cooling off. And so you're going to have to count up for some of that mass being evaporated off. So this is where this is really coming from, where we explained how it was the heat of vaporization value multiplied by the molar weight that we found as well. So that's going to be for the second differential equation. Now we just have the third one to go through, which is the rate of change of the temperature of the gas with respect to it climbing up the tower as the water adversely goes down and trickles down off of that. And so this DTG we also calculated in the last part of the exam, where it's going to be the specific area multiplied by the heat transfer coefficient. This is all going to be divided by the gas flow rate, the total mass gas flow rate. Also going to be divided by the heat capacity of the gas phase that's going to be there, and that's going to be multiplied by the difference in temperature values. So there we go, and that should be the three differential equations that we got all the way back from part 4 of the equation. So if you have any issues on trying to figure out how we got these equations or where they got them from, we derived and got them from part 4 of the exam, which would help explain a lot more where we got these. And so now that we are done with setting up this function and this equation, or it's not called an equation, what's it called? Formula. It's calling this formula in the code. And so now we have this all set up. We wanted to be able to return the values that we have at hand. So like the dy, dwt, and the dtg, the rate of change between the mole fraction, the rate of change of the temperature of the water, and the rate of change of the temperature of the gas. We want all three of these to be returned as our values. So we want dy, dtw, and dtg. So these are going to be our values that are going to be ran. So I just want to shift into this and make sure and see if they run. So everything looks good there. Well, in retrospect, it looks good. But we know that as of right now, these values are not being converged to the values that we intended. So currently we're going to have to use these guesses that we already found to try to help with what we were getting, but they are not converging to the points that we know they need to converge to. So we need to set up the second formula here where we are going to converge the feeds. Feed. I'm just not going to use any capitals. That's going to suck. Error. Converge feed error. And I'm just going to leave it as this. And I'm going to use, let's just use x. Let's just use x as the second variable that we're going to be calling. So this is going to be the formula that we're going to call for whenever we need to use this. Notice how I didn't explicitly say this, but I indented everything else over so that becomes an embedded formula, and it will call to this automatically whenever we have to cycle through this formula. And so one thing we want to do is that we want to set up our mole fraction exit value to be the first value in this array that it's going to be generating. So we want that to be the x0, representing the first value. And we also want to set up the gas temperature exit value as well for the exit feed, and this is also going to be the input into that same array, but it's going to be the first value in that array. So now that we have this, I hope this is not embedded inside of it. No, I'll just have to back it out. So anyway, now that we have this, we can now set our sole variable that we set up to that should not be capitalized. Whoops. That's positive. Yeah, so now we can set up this sole variable to be very close to, not very close, I don't know what I was going to. But we can pretty much use this as solving our IVP values and getting those values in return and getting them to actually condense down to this. So before we actually set up our return values for this designated function or this formula, we'll set up this solve IVP, solve underscore IVP. So what we want this to do is that it's going to store into the sole variable the solved values of the solve IVP that they actually converge to. And so we want it to solve, it's going to call this equation whenever we need it to, and that's going to be going from the 0 value where it's starting to the height, as that's the independent variable value that's actually ranging. Then we want to put in our three variables that it's going to be calling to, which will be these three right here. So that's going to be the y exit, which is going to be our guess that we have currently from the feed, our TW feed, which we actually know that's given to us, and the the gas exit feed, which is also going to be a guess. So now that we have these three set up and we have our given values from what we wanted to solve for, we need to go through and do our method, which we actually, I don't think we actually need a method. We just need to do our dense output, don't we? Yeah, we just need to do our dense output. And we need to put this one as true. And we also need to, do we need to do anything else? We need to close that off, that's for sure. And then we're going to take these values and we are going to store them into that Z plot, the array that we made previously, and that's going to be helping us there. So that's where we're going to store all these values, and we can just go back and end up calling for it for future reference if we need it to be. And so now that we have this done, we can actually go through and set up our return for that second formula that we're calling to, and we want to return the sole solution variable values for 0 and -1. This is because we want the last values in that array, and so this will be taking that last value from the first column of that array, and it'll be doing all the way that. And then we want to subtract from the y feed mole fraction feed, so this will actually be giving us the value of what will be left at the very bottom of the cooling tower and that designated area where we're looking at the rate of change. And so that's pretty much going to give us whatever value we are expecting as it progresses through. And so the other value we wanted to return is the solution of the third variable, which is that gas constant, not gas constant, what am I saying? Temperature of the air feed, or the gas feed, as it's progressing down through the to the cooling tower. So now we have that. We are getting pretty much returning the values of those two guesses that we don't really have. So we're taking more accurate guesses on what they are going to be as they exit the system. And so this first one, like I said, is giving us the mole fraction of water as it's progressing downward through the system. And the second one is giving us back the values of the temperature of the gas feed as it's going up the cooling tower. And before we can actually go on to our next set, we actually need to go up here and we need to set our global solution. So that I can call back to that without actually ever even needing to lock it off. Not match out our indentation. Oh, whoops. Does that help? What? Okay, how about we just get rid of that for right now, and I'll go back and put it in before we end. So take that out. Does that still work? What's going on here? Is that the issue? Yeah, I'm confused because that's supposed to be an embedded equation, that's why. I'm very confused why it's an issue. Because I have why exit defined right here. Oh, that might have been the issue. What? What is this issue? Unented does not match outer entities. This is error. It's pretty much what it's telling me is that it does not like the fact that I am pretty much doing that. Let's do this. I want to find that same equation again. DYTWTG. Input's going to be Z and V. Yeah, what the hell does that mean? Okay, so yeah, that's going to be the issue. So now once again we have this issue. The thing is that it is defined up here. That's where the issue I'm having is because when I try to embed this whole thing, indent, I get left with the same issue. Oh, this is frustrating me. How do I just fix this issue? So it is defined though, it's right over here. It should be defined though. It is defined. Do I need to call the function? Is that the issue? Should be cycling through that. Storing against Z. Why is it saying that it's not? Why is it saying why it's not defined? Can I change this like to Y exit? Is that an issue? Why is it saying it's not defined? I don't know. I'm not gonna be able to solve that mess. It's just frustrating. How would I remove this? There's no issues there. Actually, it's not defined. What the hell? Is there an issue with I'm very confused. Is this where I need to see when I put the global song? Oh my god, I'm about to lose it. I fucking hate this. So once again, just having a bunch of these issues. This is so freaking annoying because I know how to solve the rest of it. I just cannot get this to freaking work. Because it comes all the way down here. Even when we get rid of the global solution, come all the way down here for this solution. I need that value to occur. I just don't understand why y-axis is not defined, but it's literally defined right here. Well, these have nothing to come to you. I just don't. Doesn't seem like it's calling to it. Frustrating. I'm just going to go through and code the rest because I know how to do it. So the next part that we're going to have to do is we need to go through and do a root function, and we're of this the formula that we just made up there, where the converge feed error is going to be used to solve that. What we're going to use as our variables is we're going to use the y out guess that we used previously. I don't think that's right. Oh, yeah, they're all. That's how it was. I'm using guess, and then also tg out guess as well. And of course, I used the capital for that one. So these will be our inputs for the root solver, and see, that's the issue. It seems like it's not going to this equation up here. Something is frustrating. Let me just do one thing. If this doesn't solve, then I really have no idea what will. So I'm just going to retype it all into the same box. Define converge underscore feed underscore error. We'll take that and xvd components. Y exit is going to be the first thing in that array. Converge the gas exit will be the second in that array. So now that we have that, also want to define a equation tg, then put in the variable c. That's the best one to catch us. This doesn't work. I generally don't know what will. So don't have freaking. Or something else with this. Alright, so I don't know what that was in that, but thank goodness that's solved. That was giving me a headache just staring at it. So I guess I'm going to take it into account that this is all good for the time being. No, I don't even want to mess with this anymore. I'm just not even going to touch it for right now. So, alright. So now moving back on, we have the root problem, where we pretty much have it taking in, which should be our two, saying that there's, takes one positional argument. Yeah, what's wrong with this now? Oh. It's because I didn't put my comma. What do you mean CW is not defined? Yes, it is. Oh, wait. CWG? Where's C? Line 13. CG. CW is not defined. What's I use for that? CW. Ah, so see, that's the issue. So it was which equation is defined? CG equation. So I left it out. So right there. So C1 or which one do I need? I need the gas water phase. So there we go. That was another issue I did not even expect to encounter. Oh, thank goodness. Alright, so that actually finally worked out, and we are given the roots for the values that we have. We have all this and all the stuff that we want for the differentials. The last thing we need to do is go through and make our figure. Thank goodness. So we're going to start by making the subplots. So it's going to be, our figure is going to be stored into the make subplots function, where we want rows to be equal to 3 for our 3 variables, and we only need 1 column. And so now that we have that, the last thing I really need to go through and do is just add in our 3 variables to each of the lines. So pretty much x is going to be equal to the z plot, where we have each of those individual 21 linear spaced lines placed around the x-axis, so that'll be our x. Our y is going to be the solutions between first column, which will be our mole fraction, and then this colon pretty much represents it being able to cycle through each of those until the very last value in that array. We just need to change the name of each of these values to represent what they really are. So like this first one's going to be the mole fraction, so I'm just going to put it as YW. So I'm going to put a little y because everybody knows what little y is. And then row equal to 1, column equal to 1. So now that we have that, and I can even, to make this go by a little quicker, because I've already spent a lot of time just troubleshooting those 2 issues that we were having. We can go through and copy and paste these. The only thing that we need to look at and change are where we're getting the data from for these arrays. So that'll be 1 and 2. We also need to change the rows. So this will be 2 and 3. Excuse me. And the actual names of the other 2 variables, which are T and temperature of water and temperature of gas. And so everything was done correctly, which I'm really hoping it was, but go figure it's not. Name solution is not defined. So this is where I actually need to go in and put in the global solve value right before this equation. Q. It's never going to be easy, is it? It's never easy, is it? I'm not seeing what the issue is here because that looks correct with me. I just don't know why it's not defined. What is wrong with this? It's not defined. It's literally defined right up here. Do I need to rerun that? There we go. Okay, I just didn't rerun the root solver. Gosh, I'm just thankful this is over. But yeah, so this will actually give us the values which we pretty much did expect. A lot of these make sense. As you're progressing across those 20 meters of the cooling tower, you expect the mole fraction of water to pretty much decrease, and it's going to continue decreasing until it reaches 0 across the 20. Same with the temperature of the water. The temperature of the water is going to decrease, which makes I had to have messed up a negatives because this should be it should be inverse. This should be decreasing while this increases. So I must have messed up a negative somewhere. No, I don't think so. But yeah, so this pretty much concludes part 5 and exam 3 as a whole. I hope you enjoyed, and I hope to not have to do one of these again. Thank you.